Hi, I'm Dan. I'll be talking about detecting confounders in multivariate time series using strength of causation. This is joint work with Yuhao Liu, Chen Sui, Kurt Butler, and Petr Juric for EUSIPCO 2023. We'll start with the problem of latent confounders. Many scientific questions are of the form, does X cause Y, where X and Y are variables of interest? We tend to express this in a graphical format, where X and Y are nodes, and a directed edge between them denotes causation. This is already hard, and in some senses more difficult than statistics, but has been widely studied over the past 100 years or so. This is made more difficult by confounders, which are common cause variables that can create spurious statistical relationships between X and Y, even when no direct causation is present. Fortunately, if confounders are known and recorded, we can adjust for them in observational data. This is worse, though, when the confounders are unobserved, in which case they're called latent confounders. This breaks many of the assumptions of modern causal inference, and the focus of this work is to detect when this may be the case. Previous work on latent confounders will be broken down into structure learning and confounder detection. In structure learning, the goal is to find a modified causal graph with possible confoundedness indicated. This includes constraint-based methods, such as the fairly classical FCI, score-based methods, or asymmetry-based methods, as well as a few others. Some extensions to time series are also available. For example, LPC MCI is a constraint-based method for time series, and var-lingam is an asymmetry-based method for vector autoregressive signals. Confounder detection, on the other hand, is comparatively less explored, and the goal here is to detect the presence of a latent confounder without necessarily learning the entire causal graph. By defining a structural coefficient of confoundedness, there's been work in estimating confounders using spectral methods, or relatedly with independent component analysis, and using the algorithmic Markov conditions. Some information theoretic techniques have also been employed. In this work, we make extensions to time series using latent variable models and the to-be-defined differential causal effect. To review structural causal models, these are a framework for us to think about causality in, and we can understand them through a causal graph and structural equations. The causal graphs are fairly intuitive to read off. So the arrow from Y1 to Y3 denotes that Y1 causes Y3, and the lack of an arrow from Y3 to Y2 denotes that there is no causation there. If we assume additive noise, then we can write down the structural equations of the form Yi is equal to a function Fi of the parents in the graph plus noise epsilon I. However, if a latent confounder is present, this structural form may no longer hold. For example, here, yi is now a function fi of the parents as well as z plus epsilon for y2. SCMs for time series are slightly more rigid because we additionally have the arrow of time, which simply says that any variable in the current present cannot affect anything in the past. To this end, let yt be a time series with observed parents xt and unobserved parents zt. Then we can write down the parents of yt as yt minus, xt minus, and zt minus, where each yt minus, xt minus, and zt minus are exclusively taken from the past. Then our structural causal model becomes yt is a function of the parents, or a function of y, x, and z. Differential causal effect will be used in order to detect relevancy of latent variables. So our approach consists of first learning a latent variable model and then checking the causal effects of the latent variables to determine whether or not they are causally relevant. One measure of causal strength is the differential causal effect, or DCE, which takes a partial derivative of the learned structural equation. The intuition here is that for a variable x t minus li to affect yt, it must change it, i.e. there must be a non-zero derivative. Since we'll be using LVMs, we won't be able to learn unique latent variables, and we'll only have them up to diffeomorphism. But a key idea here is that the zeroness of the DCI is invariant to a change in coordinates. So for example, if dy t dz t minus I is 0 in one coordinate system, then the change of coordinates will not affect the zeroness. The DCE will still be 0 in the other one. Gaussian processes are a tool that we'll use for latent variable models, and they're a Bayesian non-parametric framework to model functions. A GP is uniquely specified by its mean m theta of x and covariance kappa theta of x and x prime. Kappa theta is often called the kernel with respect to kernel machines. The vector theta here is a set of hyperparameters which are fit according to the data after we specify a specific family of kernels. If this is the case, then we write down that f is GP distributed with mean m theta and covariance kappa theta. Formally, this is a prior distribution that we'll use for Bayesian inference. And without loss of generality, we can write down that m theta is identically 0. Since we're doing Bayesian inference, we now care about the GP posterior predictive. If we place a Gaussian likelihood on the data, then the posterior predictive of the GP is also a GP. For this, let x and y be training data, and x star be test data, and let k, x, x prime be a gram matrix with respect to the covariance function kappa. Then the mean of the posterior predictive is given in terms of a cross covariance term, as well as an inverse covariance term with the data. An issue here immediately is that while this is an analytically tractable expression, it includes the inversion of an n by n matrix, which is an n cubed operation. With large n, this quickly becomes impractical. One method to address this are random feature-based GPs. So if kappa only depends on the difference between x and x prime, then it's called stationary. And Bachner's theorem says that if we have a stationary kernel and the PSD S of v exists, we can write down kappa as an integral over the PSD. Using this, we can approximate kappa using a Monte Carlo approximation. In particular, let Vj be frequency sampled from the PSD, then kappa is given as phi v of x transpose times phi v of x prime, where phi v is an embedding vector based off of random Fourier features. The GP and its derivative are then approximated as follows. We note that the GP is approximated directly as a linear relation, and the derivative is easily computable. For a problem formulation, let yt be the target time series, let xt be other observations, so another multivariate time series, and let zt be a multivariate time series of latent variables. For modeling, we'll consider a maximum time lag. For example, Lxx is the maximal time in which x can influence itself. Lxz is the maximal time in which z can influence x, etc. And we use the notation w subscript I colon j for the subsample of a variable w from time I to j. Then our model consists of unknown functions f, g, and h, and white Gaussian noise u, v, and e as follows. Z is a function f of zx and y, x is a function h of zx and y, etc. We'll give each function a GP prior, and then our goal will be to determine which variables exhibit non-zero strength of causation on yt. In particular, we'll care about which latent variables exhibit non-zero strength of causation on yt. Our proposed solution revolves around feature-based GPs. In particular, if we use feature-based GPs and the linear embedding that they give, we could write down the state space as follows. We'll assume that the columns of capital eta, so eta 1 to eta dz, are assumed to be mutually independent. This is equivalent to assuming that each of the zt's are independent. Then we can dynamically track theta and h throughout time. The idea is to use a particle filter on z and a bank of common filters for theta and h. So what does this actually look like? At each time step, we resample zt, then we update h and theta. We can view this either as Bayesian trigonometric regression or as common filtering. Then we reweigh zt particles based off of the negative log likelihood. We estimate z hat of t, and we repeat. For our numerical experiments, we first generated 8,000 samples of the following signal, where zt varies throughout time and directly influences yt. This is shown in the causal diagram to the right, with estimated and actual DCEs shown in the bottom right. Notably, the DCEs on observed variables reflect the true data generating process. So in particular, the red solid line is close to the red dotted line, and the green solid line is close to the green dotted line. And while we can't directly interpret the scale of the latent DCE, we can interpret that it is non-zero, which indicates that there is a latent confounder. For our second numerical experiment, we chose a slightly harder state space model where there are two latent variables, of which one directly affects YT up until time 2500, after which that causation disappears. Notably, the estimated DCE is 0 in one dimension, so we correctly determined the dimensionality of the latent confounder. And additionally, the estimated DCE falls after 2500, eventually getting towards 0, as in the generative model. This shows that we can find non-stationary causalities. In conclusion, determining causal relationships is a common scientific problem. This work addresses the detection of latent confoundedness in multivariate time series, the exclusion of which is a common assumption in modern causal inference. We use random feature Gaussian processes and filtering techniques to estimate a latent variable state space model. Then we test the latent variables for strength of causation, determining whether or not there is a latent confounder. This method is able to dynamically detect latent confounders in multiple synthetic datasets. Thank you.